All right, so I'm going to go ahead and get started. So hello, everybody. I am Rob Knop, otherwise known as Prospero Frobaz, and I have been in Second Life for a million years. Not strictly speaking a million years, but more like 10 or 11, actually. I think I'm pushing 11 at this point. And I've given a lot of astronomy talks, and here's another one. So the title was Black Hole Demographics. At least that's what went out. And so then I have this thing where I usually change the title before I make my first slide. And then my friend Darcy was complaining that I had three prepositions in a row. So, of Outen. So you can think of this as the bad grammar title. What black holes do we know of out in the universe? So you have to say it with the right pause and the right tone in your voice to work. Also, this picture I found online at the Blender artist site. Made by the guy Black Rainbow. I was actually searching for pictures of the interstellar black hole from the movie Interstellar, and this is not from the movie, although it looks like it was. This was a rendering that this guy did in Blender, trying to replicate the black hole from Interstellar, and it's pretty impressive. It looks very pretty. I will show you my rendering of a black hole in Second Life later, and while it's going to be of technical use, it's not nearly as pretty, but you'll see that at some point. So, it turns out when you say black hole, you could mean different things depending on the context you're talking in. Originally, black hole was what we call general relativistic or theoretical black holes. General relativity, which describes how things move under gravity, predicted if something is dense enough, there will be a region around it that nothing, not even light, can get out of. And that region is called the event horizon. So black holes don't really have a surface. They just have this sort of point of no return, this area in space or volume in space, that if you go inside the volume, you're done. You will never get back. Sorry. And that is called the event horizon. And so here, this is my Blender rendering of a black hole. See, I did that in Blender. It's not as pretty, but whatever. This is often a picture you see, and I'm going to talk a little bit more about this picture in just a couple minutes here. And this picture actually was the distances I made and the circles and the lines I drew. I actually did some calculations from GR to get them right. In contrast, when we talk about astrophysical black holes, that's a slightly different thing. Maybe. I mean, maybe it's exactly the same thing, but when we say we are very convinced that something is a black hole, it doesn't necessarily have to be exactly the same thing as what general relativity predicts. Now, one of the arguments that's made that this is a GR black hole is that we have no idea what else it could be, and that if GR is right, it has to be a black hole, because nothing, if it's that dense, it is a black hole. But what they really need to be are very massive, very small objects that are too massive to be a neutron star and are too small to be a star cluster or something like that, and that emit no light themselves, which would, rule out a star cluster. They emit no light themselves, and then we see, for the most part, with the recent exception of LIGO, we see black holes only by the way they interact with other things nearby. Stars, gas, that kind of thing. So, black holes exist, yes, absolutely. We've known about this for a long time, and as Vic said, Cygnus X1 was one of the very first. In fact, I think that was the one that Stephen Hawking conceded his bet on. He and Kip Thorne had a bet about whether or not black holes exist, and Stephen Hawking bet that they didn't, because so much of his work was based on black holes, he really wanted them to. If they didn't exist, he would have been sad, so he thought, well, at least he would win a bet to have some consolation. But he did concede that bet. And he did it based on Cygnus X1. The evidence there he thought was convincing enough. So yes, we see lots of things. We know black holes are real, but we don't necessarily know they're exactly GR black holes. They just have to be extremely compact, high-gravity dark objects. So that's a subtle difference, but it's kind of important, because we say we know black holes exist, but we still sometimes entertain the possibility that these quote-unquote black holes aren't exactly the black holes that we predict in general relativity. Several years ago, this would have been probably 2011, long time ago, I was in the Netherlands with, some of you may remember Simone, who was what was his? I don't remember what his Second Life name was anymore. One of the Mica founders. I was out there working with him and some other people on the software package Amuse. And while I was there, Kip Thorne happened to be there giving a talk, so I went to see Kip Thorne's talk. Yeah, I don't remember what his Second Life name was though. So Kip Thorne was giving a talk, and he was talking about, and he came up with this Greek name Bathroi, and I don't remember what that is, but maybe Gumby Wumby can tell us what Bathroi is in Greek. And he was saying, what sort of gravitational wave signatures would these things have if they were different from GR? And it was a theoretical talk, right? So we entertain the idea that they're different. So it's important to realize that. All right, now, general relativity is the theory that predicts black holes. It is also our theory of gravity, our modern theory of gravity. It describes gravity not as a force. Newton's laws, and we still talk about the force of gravity, because Newton's laws are plenty good enough for almost everyday use. In fact, they're good enough to send spacecraft to the Mars. You like that? It's like the Earth. If I say the Earth, I have to say the Mars. So Newton's laws are great, and that describes gravity as a force, but general relativity doesn't. What general relativity has a completely different description of the universe. It says that what we think is the force of gravity is actually just a manifestation of the curvature of space-time. And I'll try to describe what that means in a moment. So there's two parts. One, when you quote-unquote feel gravity, what you're really doing is feeling the curvature of space-time. And then two, Einstein's field equations describe how does that space get curved, and if there's mass present or if there's energy present, that causes space-time to curve. And so there's sort of this dynamic back and forth between mass causing space-time to curve and the curvature of space-time causing mass to move differently. That if you are not too dense and if you are not too fast, right? So your density has to be a lot less than that of a black hole and your speed has to be a lot less than the speed of light. The motions you get will be exactly the same as what you would get from Newton's laws. Yeah, I'm dense a lot of the time. But all right, so how can curved space make things be like a force? Well, so here's an example of how motion in curved space would be different. That's what I've drawn down here. Imagine that the world is the surface of a sphere. So you can only move along the surface of the sphere. Now, one of the things we know in our world is that if we make two parallel lines and you really go straight, those things, the two lines will eventually leave the surface of the Earth, right? Because the horizon will kind of duck down and the line will continue on into space. So that's not what I'm talking about. I'm talking about if you go forward, you have to go with the curve. And you're not even aware, really, of off of the ground. All right, so we also know that in geometry, well, Euclidean geometry, two parallel lines never cross. Well, that's what I've done here. Imagine in this spherical universe, or whatever you want to call it, you draw two parallel lines right here. So this could be just like on the Earth. If you drew a line on the ground right above and right below the equator, if you draw two parallel lines, they will both be going due east and due west. If you make those lines go as straight as possible, it turns out they won't stay at the same latitude. If you work out the geometry for what is as straight as possible, they will both inscribe what's called a great circle, which is a circle that goes all the way around the sphere with its center at the center of the sphere. And the only way for these two circles to both do that is if they cross at the equator in two places. So these are two lines that started parallel, but then did not stay parallel. And so that's one way you can imagine understanding curved space is geometric things will be just different from what happens in Euclidean geometry, what we think of as normal geometry. And you'll notice the two things came closer together. So this could be what you might have interpreted as a gravitational attraction. It's actually really just space-time is curved. So when things go in straight lines, they end up closer together than they would have if space-time hadn't been curved. Right? So that's basically the idea of general relativity. Now, general relativity then predicts black holes. And so black holes or this theoretical construct. It's based on this thing called the Schwarzschild metric. Basically, that describes what is space like around a spherically symmetric star. It applies in our solar system. The sun is not exactly spherically symmetric, but it's close enough for purposes of GR that this does pretty well. And with this metric, you get a prediction that if you have something, an amount of mass, and all of it is in a radius smaller than this, what this formula gives you here. So G is the gravitational constant and C is the speed of light. If you have enough mass inside that radius, what you will get is an event horizon at this radius. And then that's what we would call a black hole. Specifically a Schwarzschild black hole, it's a non-rotating black hole. If they're rotating fast enough, then this description starts to break down, and there's a much more complicated description GR has called Kerr black holes, but I'm not going to talk about those because the concepts will be just fine with the simpler version. So, general relativity predicts this. It also predicts that there's a singularity at the center, and that singularity is a scary kind of thing. Basically, it means that our physics is kind of broken down. Densities go to infinity. We don't understand how it works. Quantum gravity has to matter. Anyway, scary stuff happens. But we have this advantage that there's this event horizon around it, so we can't even see it. So we're free to not worry about it. And that's what we're going to do. Now, here's the thing. When you look at this picture, a picture like this, which you say, oh, look, that's a black hole. And people will sometimes make an analogy with general relativity saying, oh, it curves space-time. Just like if you put a bowling ball on a trampoline, it'll cause the trampoline to be curved. And you think, oh, okay, that makes sense. So because things are heavy, if you put them in space, they push down on space and cause it to curve. And no, that's not what happens at all. And so these things can be very deceptive. And what's deceptive about that is you look at this and you see, oh, yeah, that looks like a black hole. You're going to fall down into the thing and whoop, there you go. And that's wrong. This thing doesn't actually directly tell you anything about the gravity itself, and doesn't actually even tell you that you will be pulled down directly in. It can tell you things about if you're passing the black hole, how will you bend? But it doesn't tell you exactly that you would be pulled in because there's no time information in this whatsoever. So if you're interpreting this as like a drain, you're interpreting it wrong. And unfortunately, that's how it's almost always interpreted and even described by people who know what they're talking about. So what I'm going to try and do is see if I can tell you what this really means. So to start with, I'm going to res out a little guy here. Here's my model of a black hole, and I've drawn a grid around the black hole. I'm going to raise it a little bit, and I'm going to tilt it towards you so you can see it better. So if you want to zoom in on this thing, see if the texture reses, you say, hey, that's great. It's a black hole. It's a black sphere, and I've got a grid around it. It's just polar coordinates around it, and it's all pretty exciting. And I'm going to try and do a thing here, and let's see if this works. I'm going to use a little pointer here. All right, so we'll see if this pointer thing works very well. But if I can point right at one of these little intersections, that didn't work. Let me try that again. Pointer first. Did work. All right, so, well, almost. So it looks like I'm trying to point right at one of the little intersections of those. So if you go around that circle, you can figure out how far you have gone. Just count, I don't know, lay down a bunch of rulers or lay out a gigantic tape measure in a perfect circle, or however you do it. You can figure out how far you've gone, and hey, great, you've gone that distance. And then if you go to the next circle in, and you go around the circle and say, hey, the circumference was smaller. And then if you subtract the two circumferences, you can figure out by dividing by pi the difference between the radius here and the radius of the circle here. And you'll discover if you try to go from one circle radius intersection just radially straight out to the next one, that the distance you go will be exactly what you would expect if you took the two circles, calculated their circumferences, divided by 2 pi, to get the radius, and then subtracted them. You would figure out exactly how far you went. Hey, that's great. At least that's how it would work in Euclidean geometry. But if you try and do this close to a black hole, what you will discover is that if you go here, right, you go to one of these intersections, and you go around and you figure out what's the circumference of the circle. And you go to a closer one and you figure out the circumference of the circle. Everything is fine so far, but the distance from one circle to the next is more than you would think from simple geometry, which means that around a black hole, the geometry of this thing that I've rezzed out is wrong. Because if you measure stuff on this, you'll discover that circumference is 2 pi times the radius. Works perfectly. So if you're near a black hole, saying the circumference of a circle is equal to 2 pi its radius is wrong. It doesn't work. Why? Because space-time is non-Euclidean there. Space even, just all by itself, is non-Euclidean. So what we're going to do is, and notice here, the grid I've given you does not show all 3 dimensions. It just shows 2 dimensions. And you wouldn't look at this grid and say, oh, I can see from this grid that I'm going to be attracted towards the black hole. I mean, you know you will be because that's what happens, but nothing about this diagram says that. So this grid, I've just left off the 3rd dimension just because drawing that would be a huge mess. I've only drawn 2 dimensions. All right, so now what I'm going to do is res out another thing. And here it comes. Here is my other thing. And it should res pretty fast because it uses the same texture. Hey, look, it's a 3D version of the picture that I've shown. So this was my Blender thing. Right, so here it is. Now, what I want to say is that if you look at this one, the grid lines are exactly the same as the grid lines on this one. The difference being that the distances are correct for the grid lines here. Now, there's nothing that actually goes down. It looks like a drain, right? Look at that. It's a drain, it's a funnel, and to try and disabuse you of that notion, I'm actually going to turn it upside down, and it still works perfectly, right? It's just as good a visualization like this as it was before. It still works as a Venn diagram, right? So, but see, if you think about it, you know, the circle circumferences are all fine, but if I go from one circle to another circle closer in, because of the angle, and then the angle changes, you actually have to go farther than you would have just going straight towards the center of that circle. So it tells you that the radial distances are greater than you would expect from the circular distances. And that's what this diagram tries to show. It does this by taking non-Euclidean geometry. It takes a 2-dimensional non-Euclidean geometry and embeds it in our 3 dimensions by just coming up with a 3-dimensional figure whose geometry is the same as the 2-dimensional non-Euclidean geometry of the piece of space you're embedding. So there's nothing 3-dimensional about this guy other than we used the 3rd dimension as a visualization tool. Now, what's interesting about this talk is that usually when I do this, I have diagrams like this one here, which I say, oh, we've embedded it in 3 dimensions. And then what have I done? I've put a 2-dimensional slide up to describe the 3 dimensions. Oh, well. But here's what's great. Right now, I have really made this truly in 3 dimensions. So it really is a 3-dimensional embedding. Although, and now here comes the scary thing, the screen you are watching it on is 2-dimensional. So maybe it's not any better. But you can alt zoom on this and look around it. But I would say there's another difference too, is that this picture over here really is just 2-dimensional. This item really is 3-dimensional, and now here's where Darcy's going to pick on me, insofar as it actually exists. Does this thing actually exist? Well, that's a hard question. It turns out finding out if anything exists is a hard question. I learned this at a talk recently. But does this thing here, this embedding diagram I've created, have any physical reality? Well, I don't know. But I was, insofar as it exists as a 3-dimensional object because its fundamental description are numbers in computers, including all of your video cards and all of your computers by now, as well as servers, that describe the relationships between 3-dimensional points in space. So it really is a 3-dimensional thing. Anyway, so that's what these embedding diagrams, as they're called, that you see for black holes, they're not trying to show you stuff going down the drain. They're trying to convey that the geometry is different. And so this region of space around the black hole has the same geometry as the surface of this figure over here. That's what it really means. So I'm going to pull my pointer away. Here and make it stop freeze? Yep, it's good. And I'm going to move these objects aside, and so I can go on with my talk. In fact, I'm just going to move them back. Bye. So that's a theoretical general relativistic black hole. Oh, and I just said everything that's on this slide, so I'm going to skip it. Now, if you think about if we wanted to make observations, what kind of geometry is it called? It's called Riemannian geometry is the name of it. Yeah, I just picked a black hole up and just moved it around. Check me out. Let's see, R-I-E-M-A-N. Riemann was the name of the guy who came up with it. So I'm pretty sure that's how you spell it, but that looks spastic with a lot of N's, so I don't know. Anyway, now that general relativity has predicted these black holes, the natural question would be, oh, do they exist? So if you want to do that, you have to think, what things would we see that say it's really a black hole? And what defines a black hole is its event horizon. So really, to be a black hole, you would need to see event horizon behavior. And there are various things that happen with event horizons. I won't go into the details of them. Ask me at the end if you really want to know. There's another thing that happens called Hawking radiation, and we have not seen Hawking radiation. And we have not, well, we've sort of seen this. It's been getting better in the last decade, but these things are very hard to observe. But there is one thing that we have observed just in the last few years, is that you also predict gravitational radiation when these things collide, and you predict very specific things about what the shape of the signal you get. Right, so what we've seen, well, this first two things describe the astrophysical black holes I was talking about. Too much mass and too small of a volume to be anything else. And it's dark. So we see those two things together and we call it a black hole, even though we weren't necessarily completely sure they were the same as the GR black holes, except we have now seen gravitational waves from merging black holes, and they matched very well the predictions of what general relativity said. So this is starting to say that the astrophysical black holes, at least some of them, have to be pretty much the same as general relativistic black holes. So what are astrophysical black holes? Well, neutron stars is the densest matter we know. So what I'm saying is that black holes aren't matter in a sense. I guess they are. I don't know. They're a phenomenon of space-time. But the densest matter we know that doesn't become perverse and have an event horizon is a neutron star. There may be such things as quark stars, but we don't necessarily have any evidence that those things really exist. So we'll forget about them for now. And a neutron star is just the same. It has the same mass as the sun, more or less. No neutron stars greater than a little bit more than 2 times the mass of the sun seem to even exist. But they are packed in a radius of like 10 to 15 kilometers. So that is 1 or 2 times the mass of the sun in a city-sized volume, which is kind of distressing if you think about how amazingly dense that is. Well, so a black hole has got to be denser than that. What have we seen that are black holes? Well, Cygnus X1, which was on the the second slide, and was one of the first things that really convinced us black holes exist, is an X-ray binary. So X-ray binaries happen when you have one star that we call the donor star, and there's another star, a much smaller star nearby, and it's pulling mass from the donor star. That mass builds up in an accretion disk around the smaller thing. It's a disk because of the 2 stars orbiting each other, and there's angular momentum, and that causes hardcore calculations some other day. This geometry is actually really pretty common. Some supernova come from this geometry. Some type 1 supernova come from this geometry, except that the thing here is a white dwarf. And then it can have various different kinds of companion stars. But if this thing is really dense, meaning either a neutron star or a black hole, and it's accreting, the accretion disk gets so hot that it shines in X-rays. And then we have these 2 acronyms you'll see again later, high mass X-ray binary and low mass X-ray binary. Based on the mass of this star, is how they define it. This star can be anywhere from 1 or 2 to 10 times the mass of the sun. So if you want to know that something is a black hole, you have to find one of these X-ray binaries so that you know, oh, we've got a really dense accretion disk there. And if you can figure out the orbit, which you can do by doing timing and watching the rate at which these things appear to go around each other, you can figure out what the mass of this guy has to be. And if the mass is too high to be a neutron star, then you say, hey, we have found a black hole. And so that's the case with Cygnus X1 and a bunch of other things where we figured out what the mass was. It was way too high to be a neutron star. It is now a astrophysical black hole, sort of by definition, and we believe it's the same as a general relativistic black hole. So one example, V404 Cygnus, is a very fun little object. It's a black hole that has a giant companion, but this would be classified as I think a low mass X-ray binary because the companion has less than the mass of the sun, if I remember correctly. But the black hole itself is 9 times the mass of the sun. And this is CGI, the picture here. So what we see these things as just a point in space. We can't actually resolve them. So the information we get is by looking at how do the X-rays and the optical light change over time. We look at the spectra. We can figure out how are things moving as a result of how things change and a result of what the detail of the spectra look like and conclude it. And then artists go and draw this picture that describes what we believe the geometry of this thing is. Yeah, I know. So this guy, now with really good error bars, we know that it's 9 times the mass of the sun. This one has been estimated in the past to be as big as 14 times the mass of the sun. So it used to be considered a really massive system, but more recent estimates have it a little bit lower, but it's still pretty huge. Vic Mouse, who figured out the cutoff density? I don't know. I think a lot of people have, and it has to do with working out the nuclear equation of state, and there's a whole bunch of different models that predict various different cutoffs. And I know there was a study that I talked about probably 8 years ago where a neutron star white dwarf binary system, they used the gravitational time dilation of the white dwarf's light going through, or no, it was the other way around. It was the pulsar going past the white dwarf. They used general relativity and time dilation from general relativity to figure out the mass of the white dwarf, and then from that they could figure out the mass of the thing orbiting it, the pulsar, and that one was 2 solar masses, and that ruled out a bunch of the models. But I think nobody's model that corresponds with the nuclear physics that we know and love and use to blow each other up on Earth, as well as to do better things like generate power, limit it to something like the idea of a very heavy isotope of hydrogen, a neutron star with a +1 charge. That's funny. Sorry, I got distracted by that. Anyway, so neutron, that's where that limit comes from. So this is just one of the examples. This is an artist's conception. This is actually from a movie. If you search for NASA V404 Cygnus, you'll find the movie that this thing came from. V404 Cygnus has this feature here. There's these jets. These are magnetically collimated jets that shoot out the poles of the system. This is another thing you often see in this geometry when there's black holes present, but also sometimes around young stars, you get outflows along the poles. It's pretty common. So in the outburst, the jet gets a lot brighter. Everything gets a whole lot brighter. And in 2015, V404 Cygnus had one of these outbursts, and I think it was the first one it had in 26 years or so. And there's lots of ideas about what causes the outburst. There's a buildup of material that suddenly falls into the center. There's also some ideas that actually it may just be that stuff was hidden behind other junk, that there's dust forming like out here. Dust actually forms in the outer atmospheres of giant stars. So if dust was forming out here, some of it would get into the accretion disk and might survive in the outer part, and it was occluding some of what we were seeing. So anyway, there's various different ideas about exactly where the light came from for the outburst, but it did have one. So anyway, and that, putting these things together with various other things, well, this, you can see this mass actually came before that outburst, but that's, so we have this mass here. Yeah, a regular hydrogen-burning star is just a star. I don't know. Or a main sequence star. Here's another thing called a microquasar. So microquasars, we call this because they are very much like quasars, only a lot smaller, like a factor of 1 billion. Well, factor of 100 million smaller. So this one, GRS 1915 plus 105, indicates it has gamma rays actually coming from it. That's why it's got a GRS name. It's got an accretion disk, but the accretion disk will have a shape something like this. It may also have dust around the edge of it here, once again, for similar reasons. It has these jets coming out of it, and there are some of these microquasars where you can see jets that have come out in a corkscrew-like fashion, which indicates that the black hole is actually precessing a little bit, that its direction of rotation is not staying exactly the same, and so the jets corkscrew out a little bit. It's pretty cool. So microquasars, there's a few of these we know about in our galaxy, and they're just very powerfully emitting X-ray binaries. And they have basically the same geometry as quasars, but Vic's right, actual quasars are farther away. So this is a summary from quite a while ago. This is the last time I could find a summary with pictures of the known black hole binaries in the Milky Way. Here's another thing that's a little more, actually it's very recent, but I don't think it has everything, of compact X-ray binaries known in the Milky Way. And so just looking at it, you can see something like a third of them, between a third and a half are neutron stars and the rest are black holes. And the masses of the known ones are between 5, most of them between 5 and 12, with a couple out here at 15. So, or maybe that's 1. I don't know. I would have to look at the normalization of their plot. Looking at this, I'm guessing that means there's a couple out here at 15, but some of these masses are going to be pretty uncertain too. This is also just a visualization of the plane of our galaxy with the spiral arms drawn in. The blue circles are what's called OB associations. That's where there's very hot, massive stars. It means stars have formed there very recently, and they tend to be correlated with the spiral arms. And then the little red things are X-ray binaries and just where they are found in the galaxy. So, our galaxy almost certainly has millions, maybe tens of millions of stellar mass black holes. And when I say stellar mass black holes, I really mean black holes that are several, so maybe 3 or 4 to 12 times the mass of the sun. If they have a companion and they're accreting enough from that companion, we'll observe them as an X-ray binary. Most of them just don't have companions, or if they do, they're not accreting enough because they're too far away, so we just don't see them. Micro-lensing is another way that people have looked for and have seen a few, but most of them we just don't see directly. So those are stellar mass black holes. So our first category of known black holes are these stellar mass black holes. Now, for the second category, we have to talk a little bit about galaxies. So this is an all-sky photo from the southern hemisphere. One thing that's cool about the southern hemisphere is the center of the galaxy passes overhead at night if you're at the right time of year. So, and it really does. I haven't been there in a long time. I think the last time I went to Chile was 2006, probably. So it's been more than a decade since I've been to Chile. But when I last went to Chile, you're observing, and so you're sitting in a little room hunched over a computer. But if you have somebody else observing with you, and I usually did, I think the last time I went, I had a student with me, Andrew Colazzi, who has now graduated from grad school as a PhD astronomer himself. He was an undergrad at the time when I was at Vanderbilt. I went outside, and if you stay outside for 15 minutes, you get good and dark adapted, and it's the top of a dark mountain where professional telescopes are, so there's no light pollution there. You look up, you really see this is really what it looks like overhead. You see this gigantic band across the sky, and sort of knowing what I'm looking at, I see this is a gigantic edge-on spiral galaxy, and oh my goodness, it's really cool. So, if you get the chance, go to the southern hemisphere. And Jess, if you haven't seen this, you have to make a point of, especially now while it's warm, of going outside, getting dark adapted, and seeing the galaxy go overhead. Now, I want to talk about the very center of our galaxy, which is 24,000 light years away. Just gives you a sense of the size of our galaxy. In comparison, Alpha Centauri, the closest star, is about 4 light years away. So the galaxy's big, I guess is what I'm trying to say. If you look at the center of our galaxy, we actually can't see it because there's a lot of dust, but we can see it because we can look at it with infrared light, which gets through the dust a lot better than optical light. So the very center of our galaxy, there's just too much dust in the disk of the galaxy that blocks our view, but infrared light gets through it, infrared light, so we do that. They're still very far apart. Remember, the sun's, the Alpha Centauri, is 4 light years, which is many, 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 many times. In fact, it is about 1 million times farther than the Earth is from the sun, roughly. They're much closer together, but they're still pretty far apart at the center of the galaxy. And then, so there's this thing called the nuclear star cluster, which is just the cluster of stars at the center of the galaxy. But then if you look at the very center right here, and that's what this next slide is going to do, you look at the very center and you look at these stars. Well, this is a group, the Keck UCLA Galactic Center group. There's another one in Germany that have been using infrared observations to track these stars for almost 20 years now. In fact, more than 20 years now. It's just as this slide is as of 3 years ago. And over the course of 20 years, they've seen a whole bunch of the stars move. And that's what these plots are. These plots, these points, are points from one time to another time of the motion of these stars, and then the lines are elliptical orbits fit to those points, and they all match, pretty much perfect elliptical orbits. And from these orbits, you can figure out right here, and one of the ones that pinpoints it the best is this one, a highly eccentric orbit, although it could be highly inclined. No, this one's highly eccentric. We know this because it's sped up a lot. Right? You see these points are close together. That means it's moving slowly. When the points spread out, it's moving faster. So all of these tell us that right there has to be a mass that we're not seeing, a dark mass that is a black hole, 4 million times the mass of the sun. And yes, this still is Sagittarius A star. Sagittarius A star is the name of a radio source. Originally, it was just, hey, we see this thing bright in the radio. It's in Sagittarius. We're going to call it Sagittarius A star. And that still is this region, and the emission comes from stuff in this region. I don't know exactly the mechanism for that emission. So yeah, the Sagittarius A star region is exactly where this is. So if you have a black hole that is 4 million times the mass of the sun, its event horizon is actually bigger than the sun. If the sun were a black hole, its event horizon would only be something like 2 kilometers out. So it's tiny compared to a star. This one, about 1/5 the orbit of Mercury. So still really small compared to how far apart these stars are. If I was faster, I could tell you how far that is in light years, but I'm not fast, so I can't tell you that. But anyway, so we've got a monster black hole at the core of our galaxy. The evidence for it is extremely strong. Why? Because of this picture, because of all these orbits going around it. There has to be something that is not glowing right there, right at the spot of my color-changing laser pointer, that that has this mass. And so we're very confident that this black hole exists. It is what we call a supermassive black hole because it is millions of times the mass of the sun, but it's actually a pretty small one. It turns out that quasars, or Seyfert galaxies, and a Seyfert galaxy is just basically a weak quasar. There were times when there were a whole bunch of different names for different things, but nowadays we know they're all basically the same things with variation in terms of how bright they are, which angle we're looking at them, and maybe some other things. But they're all more or less the same thing. And what that is that, what's happening here? Okay. You've got a black hole, a supermassive black hole, and there's an accretion disk around it. So I've drawn a little disk. Then there's some gas clouds, which may just be stars with puffed up atmospheres, but there may also be little clumpy gas clouds orbiting around the accretion disk in the black hole. Then around it, there's a big torus of dust, or a dust donut, that is so thick that if you look at it from over here, you won't be able to see the X-rays, or, well, you'll be able to see the X-rays, but you won't be able to see any optical light or even infrared light from the core of this galaxy. So the spectroscopic signature will not show you what you would expect from stars orbiting this close to a black hole, a supermassive black hole. We're blocked from this point of view. But if you look from up here, you can see down into the black hole. But then another thing happens. There's these things called ionization cones, which is basically X-rays can shoot out. X-rays from the very hot accretion disk can shoot out, and any gas clouds you have out here, that's what these purple things are, by the ultraviolet and X-ray radiation, they'll get ionized, and then we'll see radiation from that. And so we have seen a lot of these, many of these, out there. With some of the closer ones, Seyfert galaxies, we've resolved some of this geometry. For quasars, for the most part, they're far enough away that it's really hard to resolve them. But all these things are right at the cores of galaxies, and a lot of them, we have some idea about the mass of the black hole, at least some of them, And these black holes are huge. They're all millions to billions of times the mass of the sun. That gravity well is what powers this. Now, not all galaxies have an active galactic nucleus, but they still have a black hole. So the difference is there enough material at the center to feed the black hole? If you have a galactic center black hole and you feed it, you get a quasar or a Seyfert galaxy. Something, basically a quasar, and depending on the rate you're feeding it and the size of the black hole and a bunch of other stuff, will determine how bright it is. Here's a few examples. NGC 4258. So if you look, so there's various different colors here. So optical and infrared tell you where mostly the stars are, because stars emit almost all their light in optical light and infrared light. The redder stars, red giant stars, actually emit a lot more in the infrared than in the optical. So if you put those two together, you see this. This is the disk of the galaxy here. But if you look in X-rays, you see that it's really bright at the center. And then if you look at radio, Vic, that's an excellent question. I'll come back to that. If you look at radio, you see that there's this stuff going on out here. And so what this is probably the result of is, and there's probably some precession going on here too, jets that have come out of this galaxy that are glowing in radio light. And then the X-ray is what's happening because of stuff coming into the supermassive black hole right now. This is another one. In this case, this guy here, looked at what's called water masers. And the advantage of water masers is they have very, very narrow spectroscopic lines. And so they can use those. The baby got thrown out with the bathwater, with the Bathroy water. Sorry, if you remember that from before. They have very narrow lines, and what that does is allows us to measure velocities extremely well. And so from that, they figured out not just, the disk actually has this warp shape, but also because they can get an extremely good fit to the velocities that they measure, they can figure out what is the mass of this black hole to high precision. And sure enough, it is a 40 times the mass of the sun black hole. So that's pretty cool. Here's another fun picture that the Hubble Space Telescope took. So Vic, yes, it does. Although the scale of this thing we were looking at previously is a lot smaller. Notice this is 0.1 parsecs here, whereas our galaxy is, 30,000 parsecs across. So this is just the disk orbiting right near the center of the black hole. But yes, our disk, the giant, big disk of our galaxy, also has a warp to it, and we've seen that in some other galaxies as well. Not Cygnus X1. This is, I think it has a name like that, but it's NGC 40. I think it's Centaurus A, actually. I could be wrong. In any event, it's NGC 4261. Optically, it's an elliptical galaxy. So that's what the white stars here show us, basically a spherical fuzzy blob of stars. That's what an elliptical galaxy looks like. But in the radio, it has these gigantic jets and lobes coming out. That's the signature of, they used to be called a radio galaxy, but now we know it's an active galactic nucleus. And the jets that are shooting out are very much like the jets that were shooting out in the microquasars. The Space Telescope was able to resolve on a small scale the nucleus of this galaxy, and you see this thing here. This is not the accretion disk. This would be the big dust torus around it. And so we're seeing something that is suggestive of the actual geometry that we expect for these things. Yeah, so why does the jets come out? So most stuff gets pulled in, but some stuff is going to be accelerated by the black hole and then funneled by the magnetic fields from the accretion disk into slingshotting past the black hole and picking up a giant. So it gets very close. It falls in very close. Slingshots, picks up a giant amount of energy and then shoots out, and then is also accelerated as it shoots out by the radiation coming off of the accretion disk. The magnetic field of the black hole then collimates it, and the whole thing shoots out. So it's a little like if you take a coat hanger and you turn it into a spiral and you put a bead that can slide along it, and then if you whip that coat hanger around, it'll slide out. It's a little bit like that, somewhat. Anyway. Oh. There's this Cormandy. This is from a review 4 years ago. So every gravitational body would have stuff if, two things, there's a strong enough magnetic field and there is material in a disk coming in. So our sun had it for a brief period at its time, because our sun's not nearly as massive, the jets didn't come out nearly as fast, so they weren't relativistic jets. But yeah, that will happen. So if you have a central gravitational object, if you have strong enough magnetic fields oriented the right way, and if you have stuff falling in towards that central object, you can get outflows. Or jets. A jet is a really fast outflow. So this is Cormandy and Ho and a whole bunch of other people have been looking at the black holes at the cores of galaxies. And what this does, here they have, this is the case where we have a decent estimate of the mass of the black hole. And you'll see there's error bars, that's what these lines are. And it correlates really well with the brightness of the bulge of the galaxy. So if you're an elliptical galaxy, it's all bulge. If it's a spiral galaxy, we're talking the bulge thing at the center of the galaxy. And there's this really good correlation between the black hole mass and the bulge mass, which gets at the question Vic was asking earlier, which comes first, the black hole or the galaxy? And the answer almost certainly seems to be both at once. That the things that cause black holes to grow, which is going to be sending lots of mass to it, allowing matter to fall in, well, is the same thing that allows the galaxy to grow. There is a supermassive black hole at the center of our galaxy, but its mass is just a really tiny fraction, like 1/100,000th at most of the mass of our whole galaxy. So even though it's giant, it's not that much. And so these black holes at the center of their thing, the black hole at the center of their galaxies are not most of the mass of their galaxies. But why does it correlate so well? Well, it also suggests that there's this whole idea called AGN feedback, that as black holes get fed, as material falls in, eventually the accretion disk puts out so much radiation that it blows out any more gas that's trying to fall into the galaxy and stops more stars from forming. So which comes first, the black hole or the galaxy bulge? Both. And their growth is linked. The two grow together. And then some of these will happen when galaxies merge with each other, like the biggest ones are almost certainly the results of several big mergers. The black holes themselves we expect also to merge, and there is hope with a more advanced version of LIGO we'll actually see gravitational waves from supermassive black holes merging, and I am looking forward to that day. Finally, there is one more category, a very recent category of astrophysical black holes. And that is, of course, the LIGO observations, which only happened a few years ago, and they've already gotten a Nobel Prize, which is really fast for a Nobel Prize. But LIGO, of course, they've been building LIGO for decades, and finally they've started detecting some collisions of black holes, and I talked at length about this a couple of times in the last couple of years, once shortly after it came out, and then once after the Nobel Prize came out. And what's cool about this is, first of all, that we're seeing gravitational waves, which is really cool because general relativity predicted them. But also that the gravitational wave signal here that starts and it gets faster and faster and then it goes out exactly matches the calculations that you would expect, right? So here, the gray line is the signal and the red line is the calculations, and they match exactly what you would expect for two black holes spiraling in on each other. So these are black holes that have been observed, and in a sense, it's like three black holes we had observed here, right? Because there's these two, and then they were gone, but now there's this one that is the merger result. These black holes, we're really sure, very much like general relativity black holes, because they're behaving in detail like they should as their event horizons are coalescing and becoming one thing. Also, the cool thing about this is some of the things they've seen have 20 to 30 solar masses, and that is bigger than any of the X-ray binary known black holes that we already knew about. So in a sense, this was telling us about a new category of black hole that we hadn't seen before. So here's the summary of what we know about. We know about stellar mass, 5 to 15 solar mass black holes. They're in X-ray binaries. We see lots of them. There's almost certainly way more black holes in our galaxy than what we've seen there, but these are the ones we see so that we know that they exist. We know about the supermassive black holes at the cores of galaxies. We see their effects in active galactic nuclei. We also see in galaxies that are more quiescent and that are close enough for example, our own galaxy, by either looking at the orbits of individual stars or statistically looking at the orbits of the stars and gas as a whole, we can see evidence and then measure the mass of black holes. So there are million solar mass or more black holes at the cores of galaxies. And then we've seen several 20 to 60 solar mass binary collisions, and that's the total mass. So when you have two 30 solar mass black holes, when they coalesce with each other, you end up with not a 60 solar mass black hole, because a lot of the mass is lost to energy in the form of gravitational waves, but something like a 55 solar mass black hole. So we know these guys exist. So these three are all things we have direct observational evidence for. The third one is the one that we have the strongest observational evidence that it is really a general relativistic black hole with an event horizon and all of that. Now, yes, there's a giant gap. What about everything in between? Why would we have stellar mass black holes and really gigantic black holes but nothing in between? And the answer is we don't expect that. We do expect that these intermediate mass black holes exist. Where do we think they exist? Well, maybe cores of globular clusters might have black holes that are thousands times the mass of the sun. We may also expect them to be tooling around near the center of our galaxy as the result of dwarf galaxies that have been eaten, perhaps. And there was actually a paper last year that suggested evidence for an intermediate solar mass black hole near the center of our galaxy, but there were other papers that suggested the evidence wasn't necessarily that strong, so I'm not pulling it out as a clear case. So we're really sure these intermediate mass black holes exist, we just haven't observed them yet. And it's just hard. So I think one day maybe LIGO will be able to observe these, but not yet. So anyway, that is what I had to tell you about the demographics of black holes. It was sort of what is a black hole and what do we know about where black holes. Oh yes, microscopic black holes. We expect there to be such things as primordial black holes. So in the Big Bang itself, there should have been produced from just high concentrations of density in the Big Bang black holes that are left over from the very beginning. And they would be a range of masses, maybe all the way up to like intermediate mass solar black holes, but some of them would have been microscopic. Now, if they're small enough, they'd be gone by now because they would have evaporated by Hawking radiation. So the really small ones, the Hawking radiation is faster and they have less mass to lose. So by E equals mc squared, they'd all be gone if they're small enough. But there may be others. There may be more moderate-sized black holes around left over from the Big Bang. Nowadays, about the only way we can make a black hole is when a star dies. And so we're never going to make a new black hole that's not at least several times the mass of the sun. But in the Big Bang, it may have produced ones that are much smaller. And so those may be tooling around. We haven't seen evidence for them, but they may well be tooling around. Okay, right. They're like flypaper. In fact, they're just what they're like is the sun covered in flypaper. So they have gravity, and so you'll orbit around them, but they don't suck you in any more than the sun sucks the Earth in. You fall in. Yeah. So yeah, this is that's kind of a cool idea that there may be a link that dark matter actually may be related to these primordial black holes. Dark matter, of course, being a big question. We're really sure it's there. We still don't know what it is. The LHC in Switzerland has failed to find supersymmetry, which would have given us a really good candidate for what dark matter is, but it hasn't happened. When I used to give talks about dark matter. In fact, that talk that was linked online earlier, I probably say in it, in the next few years, LHC may well discover dark matter, and it didn't happen. So it is wonderful that we don't know everything yet, because there's still more to learn. Although I think particle physicists are getting frustrated because they increasingly confirm what they already know and don't find unknown things in their accelerators to point to new physics. Whereas we know there's new physics, and a lot of that evidence comes from astronomy, like dark energy. Who ordered that? All right. Does anyone else have questions? Or if there may have been some questions that went by in chat that I didn't answer just because I didn't notice it as it was coming by. Feel free to ask it again right now if you want. What is my current thinking about dark energy? about the same as it was shortly after we discovered it, which is okay, why do they die? So Hawking radiation is this weird thing that happens. It's an interaction of quantum mechanics and the event horizon of the black hole in a complicated way that I do not understand in detail, but it has to do with, in quantum field theory, randomly pairs of particles, a particle and antiparticle, get created. And if they're created close enough to the event horizon of a black hole, it's possible that, it's not really right to say this, but people say this a lot, so I'm going to say it anyway, that one of the particles falls into the black hole and has negative energy, actually, and the other particle escapes, and the result is a net loss of energy or mass by the black hole. And the escaping particles is what's called Hawking radiation. So Stephen Hawking is the one who came up with this. And the rate of Hawking radiation is higher for smaller black holes, right? For these kinds of black holes that we've been looking at, the Hawking radiation is so tiny that we just won't see it. But for the really small black holes, it would be big, and as a result, they would evaporate pretty fast, at least on cosmological timescales. So that's why we would expect the small ones to go away. How much can we say about how things work at a singularity? Well, okay, so there are lots of physical theories that eventually have a singularity in them, and almost always what that means is that you have extrapolated your physical theory past the realm where it applies. In fact, we have an everyday singularity that we all, in something that we all know and love and use, and that's longitude and latitude. If you are on the North Pole, which way is north? And what is your latitude? You can't answer either of those questions because they're meaningless questions, right? You are as north as you can get. And what's your latitude? Your latitude is all of them at the same time if you're right at the North Pole. Sorry, your latitude is 90. Your longitude, I meant to ask, what is your longitude? Your longitude is all of them at once, right at the North Pole. So that is a coordinate singularity. That just means that the coordinate system we're using to describe the Earth has broken down right there. And that's okay, because there's only 2 spots on the Earth where that happens, and so we deal. The event horizon, all right, so maybe. So here's the thing, there's 2 different kinds of singularities in black holes. You may have heard that it takes an infinite amount of time to fall into a black hole, and that is wrong. That is a misinterpretation of a coordinate singularity and the coordinates that I use to talk about Schwarzschild black holes. Those coordinates go to hell right at the event horizon. So there's no real singularity there. But at the core of the black hole, there is a real singularity. So the first one is not even an epistemological limit. It's just people misinterpreted. The second one, general relativity says it's a real physical thing. Densities go to infinity. But we're pretty sure that you have to take quantum mechanics into account. So it means that it's not right there. So yeah, in a sense, almost always, if you have a singularity in your theory where things go to infinity, it just means you probably don't have, your theory is not very good right there. And so you need a better theory that would smooth out that singularity, which would be equivalent to just using a different coordinate system to describe the stuff around the North Pole, which is what you would want to do. Probably, right? Yeah, it'd be nice if it came out as a white hole, but who knows? So anyway, and actually that's kind of what I feel about the whole Ray Kurzweil singularity as well, is that his predicting his singularity means he has extrapolated his ideas about how computers and artificial intelligence work past the realm where what he understands. But because I am a grouchy old man now, that's sort of, enough time passes, you become grouchy and old. I guess you don't have to become grouchy, but it's kind of fun to be grouchy. All right, does anyone else have any questions? What do we know about quark stars? All right, so there was a brief quote-unquote discovery of a quark star. I don't remember again when this was, 10 years ago, something like that. I always say 10 years ago when it was more than a few and less than 30. Of something that looked like a neutron star in terms of mass and stuff like that, but it was not bright enough in what it was glowing, and so it had to be too small to be a neutron star. And so for all people saying, hey, look, it's a quark star. It's something that's not a black hole because it's glowing, but it's not glowing enough. And well, eventually we figured out it was just a hot spot on a neutron star. So that's why it looked like it was smaller, because the part that was glowing was smaller. So a quark star would be like a neutron star. A neutron star is, to simple approximation, a big ball of neutrons. Now, it's really much more complicated than that, but it's basically something where all the nucleons are packed together like in a gigantic atomic nucleus. A quark star would be where the nucleons lose their individual identities and break apart into just a quark gluon plasma, and that's what the star would be made out of. Now, it may not be possible for those to exist. We don't know the interaction potentials of free quarks well enough to be able to calculate whether or not there would be a stable quark star with a radius bigger than the event horizon radius of that mass. So there are various people who have models who say yes, but we don't have observational confirmation of that. So maybe there are quark stars out there, but if they are, we haven't seen them yet. Or if we have seen them, we haven't realized that that's what they are. So what do we know about quark stars? Let's see if I missed any other questions. Yeah. Well, all right. So I would say keep an eye on the Science Center catalog. There will be other talks coming up from lots of different people, and you will get notifications from Chantal and Jess, I'm pretty sure. But in any event, you will see it on the Science Center catalog, and I hope to see you again in the future. Poles of a black hole, can I say anything? Well, so what the poles are of a black hole is really just the ends of the axis about which the black hole is rotating. Now, in the Kerr metric, yeah, you can say things about the poles of the black hole, and there's some cool things that go on there. But really, what's important is not so much the black hole itself, but just the fact that its rotation and the magnetic fields from the accretion disk allow it to collimate these jets and make them very narrow. Yeah, so the jets will be coming out, and they're magnetically confined. All right, well, thank you all for coming, and I will see you all again at some point in the future. Log out now. All right. Goodbye, everybody.